Hello and welcome all. I is Nihal Purani, research scholar at Gujarat Technological University and lecturer in Electrical Engineering Department at Sri KJ Polytechnic Bharuch, would like to welcome you for this paper presentation. The title of the paper is Optimal Sizing, Feasibility Analysis and Major Issues of Grid Connected Solar Power Plant in Distribution Network. Our supervisor name is Professor Dr. Indrajit Nandlal Trivedi. He is Professor and Head of the Department Power Electronics Department, Vishwakarma Government Engineering College, Chandkheda. And my co-author and fellow colleague is Hardik M. Agrawat. He is also a research scholar at GTU and lecturer in Electrical Engineering Department, Sri KJ Polytechnic, Bharuch. So, this is the outline of the presentation. First is introduction, issues with the integration to grid, non-technical and technical, PV simulation and detailed information, Homer simulation and detailed information about the platform, simulation and results, conclusion and the references that are used. So introduction, so it is solar energy is one of the cleanest form of the energy available in the plenitude and free of cost in the nature. So the increasing growth of any country is based on the planning and efficient utilization of the conventional fossil fuel reserves along with the trending renewable energy resources. The popularity of non-conventional energy sources has excelled due to environmental concerns, depleting fossil fuel resources, increasing energy demand, etc. So the renewable resources of power generation are environment friendly and emphasized more due to its increasing popularity and growth globally. But there are several issues with its integration into existing fossil fuel network or grid network. So first of all, before moving to the technical constraint, now we are dealing with the non-technical issues with the integration of these renewables into grid. So solar irradiation is available during daytime and the insolation varies with time and location, and it varies with the hourly time and location or place to place. So this is the biggest challenge with the integration of renewable energy resource, especially solar. Second most important issue is with its capital investment. The government is offering several benefits and subsidies to increase the generation with the help of these renewable energy resources, but it is less effective even after subsidies because the capital investment cost is very high. Also, the efficiency of the solar power plant is very less and the operational issues are governed by IEEE 1547 standards, due to which several units are wasted though generated but non-availability of grid power, because as per the IEEE 1547 standards, below 5 megawatt plant is shut down when their grid power is not available. So even if your grid power is not available and solar is generating units, but it is not converted into the actual grid network, so the policy against unit cut means unit generated against unit consumed is not balanced, and the consumer has to bear this loss during these power cut issues. Another major concern is with storage of the power. There are several solutions reported in the literature, but the effective solution is available is the battery sources. The capacity of the storage increases, the cost also increases. Also, the issue with the recycling and reproducibility of this battery energy resource is at stake. So we also have to deal with the challenges. Now, the technical challenges with the issues in the integration to the grid. So first is fault current. The dynamics of the fault currents can be altered by the incorporation of distributed energy resources. Because if consider a PV systems during the daytime when solar power plant is working, it will add current produced, and hence the current carrying capacity of that feeder must be such that it allows this current to flow in the direction which is opposite to the conventional current flowing from source to load. Also, the magnitude of the current seen by the relay or fuse may vary in the network due to this varying generation or insolation at different place and different time. Reverse power flow. So now by injecting a renewable energy resource at the load end, the flow of the current is bidirectional. The conventional source forces power from source to load, whereas renewable connected at load forces it current to flow from load to source, which is the opposite direction. This causes the reverse power flow in the network if consumption is lower than the generation and injection from intermittent natured renewable energy is large. One of the major issue that is reported is protection blinding. So the integration of PV system into grid causes the protection blinding because this relay shows the only power flowing from source to load, whereas this fault is fed by this conventional energy resource as well as this solar power plant connected at the load terminal. So the fault seen by the relay is the fault current contributing by the source only, but at the fault point there are two different sources contributing the fault current. So by applying the superposition theorem at this junction, one can visualize the reduction in the fault current which result in no operation of relay. This is known as protection blinding. This issue may cause due to reduction in sensitivity of protective devices that will depend on short circuit impedances of grid side network and the DG and the impedance of the feeder to fault point. Another major issue that is in the concern with this issue of integration to grid is sympathetic or nuisance tripping, with malfunctioning of the relays. This occurs when the relay operates for the fault which is not in its zone or relative feeder. Sometimes in case of this parallel feeder, so we have drawn this parallel feeder. In this we have connected this solar power plant at this bus C. So the relay issues trip signal for upstream or parallel feeder unnecessarily and causing unwanted isolation. This will affect the reliability of the system and causing troubles to the end consumers. Now we move to this PVC simulation and detailed information available. So the generation of solar power depends on the solar radiation and insolation availability at the location. For simulation purpose, we have selected a location that is Sri KJ Polytechnic College, Bharuch, and coordinates are given below. The second important parameter is daily load consumption profile of a consumer is needed, but it is very difficult to measure the daily insolation. So the solution is to find out the average consumption by verifying the monthly bill given by the distribution company for a whole year. So the solar power generation also depends on several location specific parameters like availability of land, physical installation, temperature and wind pressure, and other environmental parameters like clearness index, albedo, optimal tilt angle, etc. is needed for the detailed simulation. Now the first step is to start with the preliminary design and choose the configuration and site. Means the configuration, that whether you are going for the on-grid mode or off-grid mode or hybrid mode, and site selection. The next step is to enter the values of the albedos and other temperature specific details. The higher voltage represents the winter operating conditions while the lower voltage represents the summer operating conditions. These are design specific software purpose data that we have to feed in the software, and these other data which are dependent on the environmental condition are directly fetched from the metronome data available from either metronome itself or NASA website. The orientation is designed such that the optimized loss factor is at 0%. For this simulation, solar panels of Topson Energy TEL24 P315 polycrystalline and inverter of INVT IMARS BG12 KT-R30 is taken. With the tool, one can design the shading scenes and perform economic evaluation, energy management, etc. for advanced simulation results. The second software is the Homer, is a tool developed for specific design of microgrids that incorporates multiple energy generation resources. It is an abbreviated form of hybrid optimization of multiple energy resources. The software is capable of feasibility analysis that shows whether it is economical to incorporate the resources for the operation of the network created or not. The simulation can be more accurate with actual data for all the components with their capacities and cost. The main aim of the software tool is to give you optimal economical and feasible result of the system created. These are the basic details of consumption yearly on the basis for last 5 years before installing solar we have carried out. These are the consumption in kilowatt hour. So total consumption of the 5 years is this, and average is 1628.71, nearly 1630 units are consumed. So for this, considering this low demand of 1630 units, we have set the PV capacity. The required PV wattage for the day is 54.33 kilowatt hour. Efficiency is 16.21% as per the data sheet. The minimum installation available at this place is 4.20 in 86 kilowatt hour per meter square per day. So area of the solar intrinsic area required for the plant is 54.33. This is available of WHPV, efficiency of the solar panel, and the available minimum installation at this place. So the required intrinsic area is 79.6378 meters square and converted into square feet. Now total area of estate is more than the required intrinsic area, because for the cleaning purposes and to remove or to avoid shadowing effect and everything, the estate area required is slightly more than the intrinsic area. So it is multiplied by the factor of 1.3. So this is the area required, and actual area from the panel that is available is 1.943351 meters square. So area intrinsic is multiplied by 80 units, that is given by the software itself. So total area required is 155.4680 meters square. So efficiency WHPV required of the plant is number of area into the efficiency of the solar panel. So 0.1621 into 155.468 give us 25.20 kilowatt peak power plant capacity. This is the orientation that we are using for this system. So we have considered the two sub arrays, and our total power produced is 25 kilowatt peak. 80 number of units are used. 26 is the tilt angle. Module area is 155 meters square. First string is 15 kilowatt peak and second is 10 kilowatt peak. In first we have sub array of 3 strings of 16 modules in series, total 48, and in second 2 strings of 16 modules and 32 is total. So these are some basic informations available for the simulation purposes. This is the data sheet or solar panel information required for the calculation purposes as well as for simulation purposes. Inverter parameters available for the calculation and simulation purposes. This is the interface of the PVC software. This is the first information that we have fed in the system. So this is how it looks. Option TEL24P315 panels are used, 16 into 3 string, first array and second sub array 16 into 2. So total is 80 modules. Total plant capacity is 25.2 and the area is 155 or 156 meters square. So this is the solar panel data sheet or information that we have fed, and this is the inverter modules that is used for this calculation purposes. This is the pictorial view of the layout that we have drawn in the system. So it is like this: 16 modules in series, one side 3 sub arrays and second sub arrays of 2 strings. So this is the pictorial representation and actual installation layout at the plant. So total 16 modules in series and 5 rows consider the total capacity of the plant. So it is module of I maximum power into 5 strings and voltage of maximum peak value, and 16 modules such connected in series. So total capacity is 25.2 kilowatt, like this. This is the simulation results, after which we are getting this simulation result. So the produced useful energy is 3.76 units per kilowatt peak per day, and the amount of energy injected into grid is like this: 34624 kilowatt hour. This is yearly injected energy in the system. We have these are some losses at different level in the from the generation to the injection of the energy into this grid. This is for 25.2 kilowatt peak system. This is again for 30.2 kilowatt peak system. So nearly 4 units per kilowatt peak per day is produced using this plant, and the amount of energy generated is injected back into the grid like this. This is the Homer interface. In this we have incorporated the data of our system. This is connected with the AC grid network, grid, photovoltaic plant or module, and it is connected with the inverter, and through inverter it is connected with AC load bus. This is our load. This is the load demand actually 54.33 that is required, or that is we have calculated till this 54.33. So the actual data is already incorporated or fixed in the network. And these are some cost parameters: the capital cost of this solar power plant and the operational and maintenance cost. Inverter cost is also considered, and operational and maintenance costs are also considered. After simulating this way, we are getting this 84.2% of total power is produced by this Topson TEL24P315 module, and we are purchasing some power from this grid, 6928 units. So total is 100%, out of which 84.2% power is produced with the help of renewable energy resource connected at the location. So the renewable energy penetration is 84.2%. So this is how the physical and compare economics. If we are considering, then the annual worth is 72,192 and return on investment period is 9.6%. So this payback period in terms of year is 7.21 years. So operational life of any solar power plant is 25 years, and out of which 7.21 years is the simple payback period. So this is less than the operational life of the solar installed at this location. So this generation or this installation is feasible, and you can go with this generation or the installation at this plant. So it is feasible to install this capacity of solar or renewable plant at this location. So this is the 30.2 kilowatt system, and out of which 82.9% means nearly 83% we are dependent on the renewable energy resources. And again the payback year is 6.29, which is less than the 25 years period. So it is a feasible solution. So now the conclusions are: simulation report suggests that the plant installed at both the locations are feasible and economic investment. Also, PVC simulation suggests that about 4 kWh per day is produced by 1 kilowatt peak power plant. This finding is very important to convince the consumer for installation as per the consumption needs. Results also show that the renewable penetration is about 80%, shows that we are majorly dependent on the renewable resources. The payback period is less than the operational lifetime of installed plant, and positive return on investment shows the cost-effective solution of the installation at distribution side as per the consumer load demand. These are some references that we have used for this presentation. If any questions, I am happy to answer the questions with best of the knowledge I have. Thank you for the patient hearing. Thank you so much.